Hi.
Hello. So our next speaker is Bernhard Ortner. He's a Chief Data Officer at Wiener Linien. He will talk about the hybrid cloud urban traffic management. Hello, Bernhard. So, yeah, you can share your screen.
Just give me a second. So, right now you should start seeing my screen.
Yes, we see.
Okay, fine. Then I will go to the presentation mode. Just give me a second. All right. So, hello, my name is Bernhard Ortner. I will present today hybrid cloud in the urban traffic manager. What can you expect from my talk? So first of all, I will present the intro, then of course Wiener Linien, and of course in traffic management, simply because from a public transit provider it's slightly different than in the private industry. Then of course I will shortly present data sources and what sort of modeling we have. Then we go shortly into data science, and finally we end up in an architectural and cloud approach. And finally, I will also provide my conclusion. So who am I? So basically, I'm the Chief Data Officer at Wiener Linien. Previously, I worked 6 years plus in consultancy in various industries, also in automotive and finance, for example. Also, I like open source, obviously, also open source communities. I've also written several books about big data and open source, and I'm obviously a speaker, as you could see. If you want to stay in contact, I've put here my LinkedIn profile. Then Wiener Linien shortly is basically, as I said, the public transport provider of the city of Wiener, also Vienna. Wien is the capital of Austria. And basically under the umbrella Wiener Linien, we operate all transit services that the city of Wien offers, basically buses, trams, metros. Nowadays we were into the media with bikes. And we're also owned by the government. This means, of course, we have to operate on a service level and not on a fiscal level. If you want to go deeper in Wiener Linien, Wikipedia is here a quite good choice. In any cases, you can also contact me if you have concrete questions. Finally, that was the short intro. Let's get started with the more funnier part. First of all, I want to outline here traffic management. What is that? How helps that? Basically, normally you want to find your fastest route away from A to B. Normally, under the circumstances of your time spent or of a current traffic situation, if there's a traffic jam, you obviously want to bypass that. How is that different to the public transport provider? For us, the most interesting question is we want to be more efficient or safer, or we want to optimize our service level. Basically, for our customers in that sense are the inhabitants of Vienna. And obviously, since we're government owned, we have more regulations than the private sector. Especially not only with respect to GDPR, but also within other laws. Therefore, our typical use case are mainly around this service optimization, improving customer service or quality, and of course, avoiding some sort of reputation loss in case something happens. And since nowadays we also address autonomous driving, means that our fleet, for example, buses, fully work in a fully autonomous way. And for example, here is a typical bus that you can at least take a ride in Seestadt. So Seestadt is a sub-district of Vienna. And this bus, for example, is fully autonomous. And I have a question to the audience. How much data do you think such a car or bus generates per single day? For example, if it drives 24/7, fully autonomous in such a suburb. Yeah, normally, since we're in big data fashion, people always think about, yeah, it should be gigabytes or even terabytes. However, the data rate itself is less than you think. Right now, it's at maximum 500 megabytes. But what is currently also quite interesting is that we have a huge variety of sensors. So classically, you would have a LiDAR sensor or even cameras. You would have also a classic temperature sensor or humidity or torque, and of course GPS. So from a big data perspective, the Volumina itself, pair bus, is not so super sophisticated. Super sophisticated in that sense is more or less the mixture of sensors that we have built in within such a sensoratory platform, I would always say to that. And next question would be, how do you think we model our data, for example, to optimize the traffic flow from point A to B? So obviously I gave already here a hint. It's already outlined somewhere here is a traffic graph. Obviously, then you would say, okay, it's basically a weighted graph on the physical properties that I've described above. For example, if GPS is not so super fast, then of course you usually assume that there is some sort of traffic jam or at least an obstacle. And from a data or from a feature engineering perspective, we tend to normalize our features and of course to represent them in a cumulative way. For example, I've put here a picture for where two lines cross, for example, line X and line Y. And normally between here, these two stations, so the green dots, for example, is a station, also here the red dots. Here, this is typically a model. And the model, as I said, could contain various sensors. And of course, especially in our domain, we want to optimize here the flow from the green node, for example, to the red node. And the cumulative way is in that sense quite important. So if something happens here at the green node, then of course here at the red ones, there's still some sort of impact. From a data science perspective, in that way, what we did here at Wiener Linien, we indexed or the edges basically, or at least the weight from the edges, and ranked then the final cumulative sum to measure the impact of the problems. I've provided here what you can see, a typically visualization of that sort of problems. And as you can see, once it happens a problem, for example, here it goes to orange in LFS2 underscore FR2 underscore 1 here at station 9, then of course it somehow propagates through the whole graph. And if it's just light yellow, then it's you're on the optimum, and if it's of course moving in the direction of black, then you have some sort of serious problems. And our main goal here is that we of course want to have here this light yellow things and not the black ones, and therefore we decided to give at least our devices, and devices in that sense, for example, are buses or metros or trains, something where they can react proactively to go here, for example, from black to gray. In our case, since edge devices are some sort critical in terms of what they have provided, at least they're directly influencing somehow human beings, and this does not only necessarily mean the driver, also it means that they are somehow influences our passengers. You have to be here in a quite conservative way. That's the reason why we decided just to put here linear regression on the edge devices, just to predict if you have, for example, this speed or these physical properties, then please either go faster or reduce speed. So we have here a chance to grab up here the misbehavior of the track. Of course, from a data science perspective, this is, I would say, yeah, it's interesting somehow, but of course, nowadays, everything has to be somehow in a neural net. From that, we also have that one, for example. Right now, we are mainly on the long short-term memory train, I would say. And here we also can, of course, make some better predictions rather than, okay, reduce speed or increase speed. However, what is here, for example, the drawback from that, or why do we have different solutions? For example, we have here the long short-term solution. We also have the linear regression solution. This is basically because we are officially stated as critical infrastructure, and therefore we enforce by law to work under any circumstances. And this also can include that the network latency is bad, or we do not have any connection to the cloud, or we do not have any connection to the cluster. And the more easier side impact of that is that we have to provide traceability models, for example, that we now prove which sort of feature has which sort of impact on the final model. And this, of course, is on a linear regression model far easier than in a neural net. Also, what comes here a little bit into the game from the design decision is that the computing capabilities of an edge node is quite limited. Naturally, you don't have any GPUs. You just can think about from an edge device from a little bit in that direction of a Raspberry Pi. And also what came, at least somehow surprised me a little bit, is that the latency requirements played at least some sort of a role in terms of if we do not have any reaction within 20 milliseconds, we are on the default path, which means that the linear regression model is preferred over other solutions. Also, since from the obligations from the law, our on-prem cluster is the preferred way for decisions rather than the cloud. Or in other words, the operational technology, our buses, our metros, our trams are the leading system, and the IT, mainly Hadoop, is following under any circumstances. So it could not be that the IT is oversteering the OT. And yeah, what finally, to sum it up, we always have to provide a basic service. For example, if some track or train is not driving, then we have a problem. But if it's, for example, slower or missing or having some delay, this is acceptable. And finally, since we are also in this quite tight regulatory system, human beings have to retain control of the system and finally of the decision. So we are not allowed, for example, to just pull the brake if the model has stated to do so. Consequently, what we did is that our cloud basically enriched the on-prem system with basically the additional cloud capabilities. For example, if you want to make a now more precise statement, we used Azure Cognitive Services, for example, for object recognition. They're quite good in that point, and this reduced basically the time to market from our digital services. Also, we used the bursting capabilities to cloud, as Stefan already mentioned in the previous talk. If we have an unexpected increase in our network traffic, we just spin up some additional VMs in the cloud. Mainly, we are using that as infrastructure as a cloud, combined with, as I said, Azure Cognitive Services as a REST. And finally, also what is quite important was quite important for us is the model deployment directly to the edge. Yes, we have that. And for that one, we just can deploy to the simplest version of that. Of course, you can think about what's the simplest version right now. It's at that point linear regression. However, that is can be oversteered at least under some circumstances via the long short-term model. If we have now, from an architecture point of view, this bubble here is basically our on-prem cluster, and this bubble here is, for example, Azure. Gateway here is, for example, the interface to the buses, and the gateway basically feeds the messages in our on-prem data lake, and we're directly replicating them in the Azure data lake. Simply because we train here our, let's say, more sophisticated models, for example, the LSTM. And for example, then once it's finished, we basically port them and operate the models basically on-prem via Spark. One of our key problems were, for example, models are not directly here portable. Docker, for example, could be a viable option. In our case, Docker had too much overhead. That's the reason why we tried to pickle them first. However, this also did not, also it worked basically. Once we tried to optimize them, of course, we then had here some problems that, for example, some functions were not properly executed or they were not basically, Spark was not able to read the Azure ML model. So one key decision that we made here, we would choose the Databricks stack in the same version as we used it here in our on-prem CDP platform. Of course, then the interoperability problems were a little bit better. Finally, what we did here is, for example, that we used the, let's say, the sophisticated model to improve, for example, the linear regression model. And yes, in that sense, we had to develop it twice. Twice in that sense that we had one model that we could ship quite easily to the edge node and one model that we could use in our cluster, for example, gaining some deeper insights. And this, I would say, knowledge in that sense, so it's not information anymore. For example, could be do not rely only just on the speed, for example, to also increase, think about of the torque could be also an important measure, or for example, the weight distribution. And then, of course, we incorporated this also in the simpler model. Once we are just here in this homogeneous encapsulated model, then of course Docker would be fine. And once we did here this linear regression model, of course, we pitched it here back as published results on the gateway, and then finally here on the bus, the driver would get an let's say a notification, please increase your speed or please decrease it. What I also previously mentioned here, that the human being should be always finally capable of oversteering the decision. This is here mentioned as monitoring and control. We have here, for example, a mobile device where you can say, no, I don't like this decision, I would like to go on my own. Or here, for example, surprisingly, I now like the English term, so I would call it just control center. And here in the control center, you would also see the actual traffic, the actual flow or the behavior of the bus with respect to the decision that has been made. And of course, it improves here also the future model building. Why do we have here a separate report and visualize? This is basically what you have seen here. This is provided to our infrastructure department because they are also quite interesting here. What sort of impact was on this and that track? How did the impact propagates? And they make the decision from a business perspective. It's worth that we improve here, for example, this station, or it's basically, I would not say waste of money, but we can push it basically in the future retrospective if we should improve it or not. So this is meant here what is as click. Finally, also since we're having here some basically arrows back to the Azure data lake, what is basically here, let's say, on the interaction with the human beings finally. So this is the more interesting, I would say, data rather than just an additional data science model. So if, for example, a model is highly anticipated, means that it has really generated some business impact, then of course we also provide here this information back to the data lake in Azure basically, because this definitely then refines here the model training, building, explorative approach from the data scientists. because what is the worst case for data science? It's obviously a model that has never been gaining business value at all. Finally, what is my conclusion? What we struggled a lot basically from a data science perspective, it was this model portability, not only just on-prem, also within the edge node. Surprisingly, hybrid cloud is still quite evolving, so there's a lot of movement. For example, Azure will soon announce Azure Arcs, so this path here will be, let's say, a little bit smoother than it is right now. So hybrid cloud in that sense is still a field that is under massive movement. Also from my perspective, simple solutions are preferred over complicated. Well, depends on what you want to achieve and depends on which sort of process do you have. At least from Wiener Linien perspective, it was totally fine that we have a simple model deployed direct on the edge, and we oversteered it basically. We are a sophisticated model. However, you have to have a fallback solution that works under any circumstances. It could be quite easy. It could be quite complex. Of course, this depends on the country you live and on your legal department. And also what I found out, address legal obligations as soon as they arise, preferred proactive and not retro perspective. Otherwise, you will end up in any, let's say, interesting discussion that you would never imagine. Finally, this was my short intro into hybrid cloud. Do you have any questions or things that you want to go into deeper?
Ran, do you have any questions?
Yes. So okay, let me ask this way. So this is very exciting, and you know, not only the technical aspect, but also the application of such systems. I didn't know that traffic management systems are this much complicated these days. So my first question is probably on the application side. I want to understand, what are your interventions? Like, how do you optimize the traffic? You see a bottleneck somewhere, you see this line is has too much traffic. What are the tools? What can you do? So one thing I could expect is to change the schedule, for example, makes a couple of things, couple of buses run faster or run more frequently maybe. But if I understand it correctly, you cannot change this very often. But on the other hand, I see that your decisions are almost like at minute level, not like for a week or for a month, right? So can you please explain what are your interventions? How do you, what does your system tell to the drivers? Or
basically, what we cannot do is obviously that we cannot change a track as you would normally do in the private sector. Basically, what we do is we, as you already mentioned, that we increase or decrease the interval. However, this will be the ultimate ratio. What we always do is basically that we tell people, as I already mentioned, just very rudimentary, either go faster or just go slower. So these bubbles here basically turn basically light yellow. What in terms of what can we do additionally, if it's more or less we're on a bus sector, then of course we can make a alternative route. This does not work always, simply because traffic jam is not just at a single street. It's more or less, you could imagine that at I would say 10% of the district. So at that point, we would violate our service agreement within the city of Vienna. Apart from that, we can in fact do quite less things, apart from making the interval more sparse or dense.
So your interventions are like at minute level, basically. You tell the
Yeah,
driver, please drive faster. Okay,
because
interesting.
this, yeah, I mean, what we have, and this is also the huge difference between the private sector. We have a station that we have to address somehow. We can go in a different sector, also in a different
Yeah,
way between the stations, but at the end, if we have to be at station one, we cannot move the station one, obviously.
yeah. I see. Yeah. Uh, okay. Another question. Uh, you have basically your own on-prem platform
Yes,
which can operate if there is no connection to Azure.
yes.
And as far as I understand from this picture, this human in the loop part, this monitoring and control, can operate without Azure, right?
Yeah,
How does it
we
work? Does it use internet or do you have some local, because this monitoring control person is not next to the bus, right? Physically.
no,
This person sits somewhere in the control center, which is on the other side of the city.
yes.
But the connection between this person and the driver, uh, doesn't it flow through a regular internet?
No, no. We are having our own. In that sense, we are having our own network simply because we are also a critical infrastructure component. We are not allowed to go over the internet. Also, what is happening here and here, it's basically then the bus or the tram. So if we cut, for example, here, also Asia and our on-prem cluster is not available, the bus itself can still say, okay, go faster or go slower. So these components are always optional. This is mainly from our requirement that we have to provide our service at any circumstances.
Yeah, but then probably it's out of the scope of this talk, but how do you connect to a bus without an internet? You should have some sort of wireless
We have
connection.
we have yeah, we have basically an own telecommunication provider that does that. But as you
Ah,
said, if you want to go deeper in that direction, it's probably one separate talk.
I
I think
see.
they just use the VLANs and from the separate VLANs using the telco provider and not mixed with the internet.
Yeah, you can think about that one, even it's a little bit more sophisticated than just having a separate VLAN.
Okay. Bernhard, Hrant, do you have other questions? Okay, so thank you for your talk. I have one question. During the pandemic of the COVID-19, the traffic from the urban traffic was used to model the spread of the virus, so to fine-tune the models which will um, uh, describe the spread of the virus. Do you use the data from your solution for that cases? Do you work with epidemiologists on that topic?
Basically, we have epidemiologists, but we do not provide any active data. So we build our own model, but we do not publish it in that direction. Because as you said, we also have to, or we want to provide any information that we can minimize those clusters in that sense.
Okay, thank you. Do we have other questions?
One more thing I wanted to ask. What kind of sensors do you have to get the data to make these decisions? So I imagine these linear models require locations of your all buses and other objects, right? But also probably some other thing like maybe cameras on the streets that capture the traffic or something that is outside of your buses, your fleet of cars, right? To make.
Right now, we are just using our fleet itself, so we do not grab any public data from that perspective. Even we have also thought about in that direction, but it's not so easy to do that in Austria.
I see. Yeah, and but your the data from your fleet is enough to make good decisions, basically.
Yeah, basically, yeah.
This is amazing.
Yeah, I mean, such sensor platform has sensor platform in that sense, it passes, I think, over 10,000 sensors. Also in that direction, if you have a bus that travels across Vienna, we are having micro local weather data. Even you would not imagine that.
I see. Okay, thank you.
Thank you very much. This was our last talk. So thank you very much for participating, and thank you speakers for their talks. I think Rand has some words to say before closing. Yes, Rand?
Yeah, so that's it for DataFest 2020 Yerevan edition. So thanks one more time to all our speakers and panelists who brought a lot of nice content to this event. Thanks to our sponsors who made all of this possible: WebFontaine, Simply Technologies, Crisp, and PixArt. So many presentations from today's from these 3 days are already put on Slack, and we will continue to ask our speakers to put their presentations there. You can still ask questions to our speakers, and we have also recorded the talks, and we're going to put them online over the coming weeks. And thanks to 350 plus people who have joined our Slack and hopefully watched at least one talk during this event. And we're probably going to do another DataFest next year, again in September, and we really hope that it will be offline this time. Thank you everyone who contributed to this event. See you next year.
Thank you.
Okay. Bye-bye.
Bye.